Chemistry, we're on to our third lesson in the electrochemistry unit. This is on electromotive force. So voltage is electrical potential. Voltage is comparable to the gravitational pull of a planet. In an electrochemical cell, voltage is a numeric measure of how strongly the cathode, that was the copper in our last lesson, will pull electrons away from the anode, which was the zinc in the last lesson. Another name for voltage used in electrochemistry is electromotive force, and that's abbreviated EMF. So here you see a table of standard reduction potentials. So it's important to understand these in doing electrochemistry. So standard reduction potentials, which are designated by the symbol E with the little circle, which means standard, it's standard conditions, and reduction. So these are standard energies of reduction. They show the voltages of different elements, ions, and common reactions. The standard oxidation potentials, which is E with the little circle and OX for oxidation, can be obtained by reversing the direction of the reaction and changing the sign. So there's really no such thing as a table of standard oxidation potentials. If you want to know the oxidation potential of anything you see there, you simply reverse the reaction and change the sign on the number over on the left. So the oxidation and reduction potential for two hydrogen atoms ionizing is defined as zero. Defined as zero simply means scientists decided that they were going to assign zero to the oxidation and reduction of hydrogen in both directions, both when it's being reduced and when it's being oxidized. So let's look at those reactions. If we take a hydrogen molecule, H2, and we take away the two electrons that it only has two electrons, you'll end up with two hydronium ions, 2H+. That is said to have an oxidation potential, standard oxidation potential of 0 volts. Now, if you go in the other direction, you take two hydronium ions and add back two electrons to turn that into a hydrogen molecule. That's a reduction because the hydrogens are gaining the electrons. That's going to have a reduction potential of 0 volts also. So anything revolving around hydrogen is going to have a reduction or oxidation of 0 volts. All other voltages, V or EMF, are measured against their ability to reduce to hydronium ions, H+, or oxidize H2 molecules. In other words, if you compare everything to hydrogen, then you can compare everything to everything else by saying, how does it compare to hydrogen? How does another one compare to hydrogen? And then that allows you to compare two different elements to each other. Okay, we'll see examples of that. For example, copper and zinc. So elements or compounds with high positive reduction potential and standard reduction potentials on the list of standard reduction potentials that you see there on the right, such as nonmetals fluorine, chlorine, and oxygen, these have high electronegativities. So they strongly attract electrons. We know that from studying the electronegativity and the ionization energies of atoms back earlier in the course. So they're going to be reduced, meaning they're going to gain electrons. They have positive signs for reduction because they are positive when it comes to reduction. That means that's naturally going to happen. When the standard energy of reduction or oxidation is a positive number, that means that is going to happen naturally. So let's look at the fluoride, the one at the very top. So that means a fluorine molecule, will take in two electrons from hydrogen. It's very good at taking electrons away from hydrogen, and that will turn it into two fluoride ions. So that means the fluorine was being reduced. It's gaining the electrons. So what that means is that happens very spontaneously. If those reduction numbers, those potential numbers over on the left are positive, that means that reaction will happen spontaneously. We talked about that in thermodynamics. It'll happen naturally. Now we go down to the bottom. Elements and compounds low on the list, such as transition metals, with low ionization energies such as zinc or aluminum strongly release electrons to become oxidized. So if you look down there, for example, at zinc, down there it's a negative 0.76. That means it's not going to take in electrons from hydrogen. In fact, it's going to do the opposite. It's going to spontaneously give off electrons. That is, it's going to be oxidized. It's going to lose electrons. So how do you know that? Well, to make that 0.76 positive, you have to turn that reaction around to make it a positive 0.76. And when you turn it around, what you're saying is that a zinc atom is going to produce a zinc 2 plus ion and 2 electrons, and those 2 electrons are going to go to the hydrogen. All right, so what you got to remember is what you want over there in that column on the left is for the numbers to be positive. The ones down at the bottom you have to turn the reaction around, reverse the reaction for that to happen. So there's the zinc, and there's another one, aluminum 3 plus. An oxidation or reduction reaction will happen spontaneously when the standard reduction potential is positive. So the ones up above hydrogen, which are all positive numbers, will spontaneously be reduced. They will take in electrons from hydrogen. The ones down at the bottom will not spontaneously reduce hydrogen. They will not spontaneously take in electrons. So you have to turn those reactions around to make those numbers down below hydrogen, down below where you see 0, to make them positive. So they're going to be spontaneously oxidized by hydrogen. They're going to give off electrons to the hydrogen. So here we see down there just above hydrogen, you have a copper 2 plus ion, and it is spontaneously going to take in 2 electrons. That means it's going to be reduced to become a copper atom. That's what we saw in our last lesson. And that happens naturally with hydrogen, so that's a plus 0.34. That will happen naturally. That's a standard reduction potential. Copper 2 plus will spontaneously gain 2 electrons from H2 and be reduced to copper atoms, just copper, standard copper, electrically neutral atoms. This means that hydrogen will spontaneously be oxidized. That is, it will lose electrons to the copper. So there's that reaction. So those two reactions go together. The hydrogen molecule will become 2 hydronium ions plus 2 electrons, and those 2 electrons will go over to the copper ion to make it a copper atom up above. An oxidation or reduction reaction will happen spontaneously when the standard potential voltage is positive. So for any of these things to happen, you have to have a positive number over on the left. Okay, I want to keep repeating that. Be sure that's clear. That means the ones down on the bottom, which are negative, if you want those to happen spontaneously with hydrogen, you have to turn the reactions around so that those numbers will become positive. That will be an oxidation, not a reduction. Okay, so now you have a zinc 2 plus, and if you add 2 electrons to it, you'll get a zinc atom down below. So that is, if it takes 2 electrons away from hydrogen, it will become an electrically neutral zinc atom. But look at what the standard reduction potential is. It's negative. That means that's not going to happen. It means that zinc is not going to take 2 electrons away from hydrogen. So the E standard reduction potential is negative, which means that zinc will not gain electrons and be reduced by hydrogen. If the reaction is reversed, then the standard oxidation potential will be positive, and the zinc will oxidize and lose electrons to hydrogen, to hydronium ions, or to hydrogen. So the zinc will then become zinc 2 plus. It will lose the 2 electrons, and those 2 electrons will go to 2 hydronium ions to turn them into a hydrogen molecule, and that will happen spontaneously. That's why the standard oxidation potential is a positive number, positive 0.76. So an oxidation or reduction reaction will happen spontaneously when the standard voltage is positive. So zinc, let's look at what's happening here. Zinc is being oxidized. It's giving off, it's losing 2 electrons to become a zinc 2 plus ion, and that will happen naturally because the standard oxidation potential is positive, plus 0.76. And those two electrons will go to the hydrogen. So it'll go to two hydronium ions. It will jump onto those hydronium ions and turn them into a hydrogen molecule. Now, let's look at the reverse reaction. So zinc spontaneously oxidizes and loses 2 electrons to hydronium. Now, let's turn this reaction around. We have hydrogen, which is now being oxidized. It's losing 2 electrons. And where are they going? They're going to copper. They're jumping onto the copper ion, 2+ ion, to make it a copper atom. And we see that that happens naturally. Both of these reactions happen naturally. Zinc gives up 2 electrons to hydrogen, and copper takes in 2 electrons from hydrogen. So that you notice that both of the reduction potential, both of the potentials, both oxidation and reduction, are positive. That means those reactions will happen naturally. So copper spontaneously reduces and gains 2 electrons from hydrogen. But look at those 2 reactions in the middle, the hydrogen reactions. They're just the reverse of each other. So what we can do is basically eliminate them, cancel them out. So we can eliminate the 2 hydrogen reactions since they reverse each other and include only, and now we include only the elements of interest, which are zinc and copper. So now you can say that zinc is passing 2 electrons over to copper directly. And the voltage, the potential difference, the voltage that you will get from that, that's the amount of gravity that's pulling those electrons, is the 0.76 plus the 0.34. So an oxidation or reduction reaction will happen spontaneously when the standard voltage is positive. So zinc gives up 2 electrons, and it does that naturally to give a 0.76 voltage, to produce 0.76 volts. And copper takes in 2 electrons naturally to have 0.34 volts. So the 2 of them together, the way we had them in the battery in the previous lesson, copper pulling electrons from zinc, is going to be a total voltage, that is the standard potential of the reaction overall, is plus 1.10 volts. And that is a known number. It's an established number for copper and zinc. You will always produce 1.1 volts when you have copper and zinc together. So both the oxidation of zinc and the reduction of copper happens spontaneously. The standard potential of the reaction can be expressed in either of 2 equivalent equations. So the potential or the voltage, the EMF of the reaction, is the potential of the reduction of the cathode, that was the copper, plus the potential of oxidation of the anode, that's the zinc. And when you add those together, you get the overall potential, that is the voltage of that particular battery or that particular electrochemical cell. So the potential of a reaction can be expressed in either of the equivalent equations. That's the one we just saw. You take the potential of the reduction of the cathode and you add the potential of the oxidation of the anode. That requires that if you get the number off of the standard reduction potentials table that we saw a few slides back, you have to reverse it. You have to turn it around and make that a positive number. Another way to do it, the standard reduction potential table lists reductions only. So this equation can also be written like this. The potential of the reaction is the potential, the reduction of the cathode. Those are the positive numbers we saw up on the top of the table. And then you simply subtract those negative numbers down at the bottom. So it's minus a negative number, and that's the reduction of the anode. Either of these are the same equation. On the one up on top, you're adding. The one down below, you're subtracting a negative number. That's also like an addition. So this form of the equation has a subtraction sign. If you use this equation, you won't need to change the sign on the number for the standard reduction potentials. Okay, so let's look at it with our electrochemical cell from the previous lesson. The anode is being oxidized. That's the zinc. So use the reverse of the reduction potential from the table. So you have to take that negative 0.76 for zinc and turn it around, turn that reaction around, and make it a positive 0.76 for an oxidation. Again, that table shows reductions, so if you want to know the oxidation of an element such as zinc, you have to turn the reaction around. I know it's a little confusing, you just have to think about it a little and get that to kind of process. So that means that the potential of oxidation of the anode, the zinc, is plus 0.76. Now the reduction of the cathode, that's the copper, is plus 0.34. That's listed on the standard, since this is a reduction, it's listed on the reduction table as a positive number. That's just for copper. Look on the table again, it's 0.34 volts. So the cathode is being reduced, so use the reduction potential from the table, which is positive 0.34. So now you see down at the bottom that when you add those two together, you end up with 1.1 volts, and up above at the very top of the diagram, you see the voltmeter says 1.1 volts. That's the potential. That's the electrical gravity that's pulling on those electrons. So the potential of the reaction is the potential of the reduction of the cathode. That's what you see on the reduction table as a positive number, plus the oxidation of the anode. That's the one you have to turn the equation around and turn that into a positive number, and that's the 0.76 for zinc. So that gives you 1.1 volts. Now, free energy. So we learned in the thermodynamics unit that free energy is what determines whether a reaction is spontaneous. It flows naturally forward. And we learned that that happens when the free energy is negative, when you have a negative delta G. So free energy, delta G, is a quantity that determines whether a physical process, such as a chemical reaction, will proceed spontaneously, naturally. We already learned that a redox reaction will be spontaneous when the potential of the cell is positive. So we saw positive 1.1 in the last slide. The relation between the EMF, that's the voltage, and the standard free energy, delta G, with the little circle, is delta G, standard delta G, equals negative NF times the standard potential of the cell. So N is the number of moles of electrons. So since we were passing 2 electrons from zinc to copper, then that's going to be 2 moles. So this is the 2 minus in our zinc copper cell. F is something new. It's called Faraday's constant. It's the number of coulombs per mole. Coulomb is the standard charge of electricity, of electrical charge. So it's how many coulombs you have in a mole of electrons, and that number is 96,485. That's a fixed value. And finally, the E of the reaction is the standard potential. So in the last example, it was 1.1 volts for a zinc copper cell. So in a zinc copper electrochemical cells, the following half reactions took place. You had the zinc being oxidized, it was losing electrons, and that was natural. So that was a plus 0.76. You had the copper being reduced, taking in electrons, gaining electrons, and that was natural, so that was a plus 3.4. So the overall potential of the reaction is those two added together is 1.10. Substituting values from the zinc copper cell, we get into this equation right here, we get negative 2 moles of electrons, because that's how many electrons are passed. There you have Faraday's constant, and then you have the standard potential of that reaction, which is 1.1 volts. And when you multiply that all together, you get negative 212,267 Coulomb volts, which is, we won't go into the unit analysis here, but that's the equivalent of a joule of energy. So it's negative 212,267 joules of energy. And there, 1 joule is 1 Coulomb volt. So an electrochemical cell reaction will be spontaneous when the potential of the reaction, the standard potential of the reaction, is positive, and the delta G, the standard delta G, is negative. Okay? Reactions are spontaneous when the free energy, delta G, is negative. This means that electricity will flow. Okay, and that takes care of our lesson on electromotive force and standard potentials of reaction.